Good evening there everyone. Welcome to Northern's Craft. So today I thought it would be better to uh, talk something very interesting. I'm going to talk about the seven important problems, or what we can say is Millennium Problem, Unsolved Problem. So one of the problem, Poionier conjecture, is solved by Grigor Perelman, that Russian mathematician, and rest six problem is still haven't solved yet. And if we are able to solve any of those problems, we are going to get $1 million with field medal, and our name will be implanted in the history of mathematics forever. So I'm not going to solve the problem, by the way. It's hard for me to solve the problem, so I'm only going to explain the problem. What is the problem? So I have done a little bit of my work in understanding these problems. So number one problem, that is bridge and I thought I was writing in something else. Shinnerton. Bridge and Shinnerton's conjecture. Shinnerton Dyer conjecture. This is the first conjecture. Then there's another conjecture called Hodge conjecture. So these are the seven millennium problems. Hodge conjecture. Then Navier-Stokes Existence and Smoothness. Then P versus NP problem. Then fifth problem is Riemann Hypothesis. Riemann Hypothesis. Sixth problem is Yang-Mills existence and mass gap. Then the last one is Poionier conjecture, which is proved by our great mathematician Grigor Perelman. So these are the seven important problems. If we are able to solve these problems, bridge and Shinnerton-Dyer equation conjecture, Hodge conjecture, Navier-Stokes existence and smoothness, P versus NP problem, Riemann hypothesis, Yang-Mills existence and mass gap, and Poionier conjecture is a solved one. This is solved by Grigor Perelman, a scientist who refused to take the $1 million from CMI, Clay Mathematics Institute. Clay Mathematics Institute still have $7 million. If you are able to solve any of these equations, any of the seven equations, we are going to get a $1 million. So by the way, it's not easy to solve any of the equations, and the only solved one till now is Poionier conjecture. In 2003, Grigor Perelman solved this. So before understanding the conjectures and these problems, we need to understand what is conjecture. Conjecture is the conclusion. Remember, conjecture is the conclusion that is preferred on a tentative basis without a proof. A statement that has been proven by a logical agreement based on axioms is a theorem. So we need to understand what is conjecture. Conjecture is a conclusion that is given on the basis of some examples and so no, without a proof. If the statement is always true, we doesn't have to prove. If it doesn't have need to prove, no, then it's called axioms. If it has to prove, then we call it an conjecture. We need to understand the difference between conjecture. Conjecture and axioms. If the statement is always true and doesn't need a proof, then it's called axioms. And if it's need a proof, then it's called conjecture. And theorems are based on particularly on axioms. And if we are able to prove the conjecture, then it becomes theorem as well. So that's why these problems, the unsolved problem, most of them are conjecture. So let's understand one by one the conjecture that we are talking. And I have tried to try to understand this equation in very easy terms. So let's understand one by one. Let's understand the first solved problem by the Grigor-Perelman. This problem is very based on particularly on topology. So basically, it's a study of in one of the particular branches in mathematics where we studies about the 3D spaces on. So the Poincare conjecture. This is solved by one of the great mathematician. Poincare conjecture. I don't want to write the wrong spelling. Poincare conjecture. Poincare. C-O-N-J-C-T-U-R-E conjecture. So basically what it says is 3D shape that doesn't have any holes. So any 3D shapes which doesn't have a hole, holes, must be a sphere. Means must be converted into the sphere. So like 3D structures like cuboid. So this 3D structure doesn't have hole. So these structures can easily be converted into the spheres. So now I am saying this in a topological term. So topological terms mean you can easily if you have a clay, you can easily convert this torus shape or donut shape, we can call it donut shape, into a sphere if we have a clay. But I am talking about in a topological term. So where it doesn't have a hole, so where it doesn't have a hole can easily be converted into the sphere without damaging its real structure. It damages the edges and all, but topological properties are totally converted from cube to sphere, from cube to this and cuboid to this, which doesn't have a hole. So this is proved by none other than our famous scientist Grigor-Perelman, now in CMI Institute, Clay Mathematics Institute. One of the pillars in that photo of this famous scientist Grigor-Perelman is there. And the sixth problem was still unsolved. So now, so this is the problem now. So particularly it says 3D shape that doesn't have any holes must be a sphere. So we can convert this shape in sphere. Consider the example of clay. Okay, we can convert the shape of this sphere into this, but when we convert the shape of the clay into the circle, the hole gets lost. Hole is not there in circle. So that's why structure doesn't need a hole in a topological term. So it was solved by Grigor-Perelman. Huge equations are there. So now the unsolved problems. I've tried to done it in very easy term. Now let's understand from Riemann hypothesis. Riemann's hypothesis. JGSIS hypothesis. Okay. So imagine you are going in a beach. Imagine you are in a beach. Okay, imagine you are in a beach and you are collecting this searching for seashells You're searching for seashells. Now you're searching for seashells and you're collecting seashells, and these seashells represent the prime numbers. Think like prime number. These seashells represent the prime numbers, which are not divisible by any other number than 1 and themselves. Okay, like 2, 3, 5, 7. These are like numbers which are not divisible by any other number than other than 1 and themselves. So now these are the seashells that you are collecting in a like beach. Now Riemann hypothesis is like a treasure map. Okay, that helps you to understand the distribution of these prime numbers. Okay, it is a map. If we solve, would reveal the secrets of these prime numbers along the scattered along the real number line. Okay, so Riemann hypothesis is like a treasure map for this, which help us to understand the scattering of this scattered seashells along the way, which will help to understand the number line where how the seashells are connected through it. So in the Riemann hypothesis, there is called the zeta function. So this is like a zeta function. Imagine like a zeta function is like a magical lens that magnifies the pattern of these prime numbers. Okay, the hypothesis suggests that the zeros of this function, wherever the zeta function is equal to 0, wherever the zeta function is 0, or we can say the hypothesis suggests that the zeros of the function, the points where it equal to zeros, are all lined up along a specific line. Consider like for example, this is the line, okay, where zeta function are all 0, so it lies in this line. So this is the thing which is like said by the Riemann hypothesis. We need to like, if it will be true, then it hugely impact the mathematics understanding of the prime numbers now. So zeta function, if the distribution of this prime number in a zeta function is like a 0 in this particular line only, then it will make a huge difference and help us to understand the computer algorithms and mathematics in deeply and more understandable manner in these prime numbers. Now let's talk about the next important conjecture. Let's talk about the Hodge conjecture, which is still unsolved. Hodge conjecture. Now think like you are building a complex structure, okay, with a Lego or Lego bricks. Okay, think like you are building a complex structure with a Lego bricks like this. Okay, you are building a complex structure with a Lego bricks. Oh, now think you are building something, okay, and then you are building in such a way like you suddenly build a very complex structure, like consider a spacecraft or something like that. This is a spacecraft and this is a very huge building of very unknown type of shape. Okay, you have built like this. Okay, so now what it says, like you start with the simple blocks, like you start with like a single block, no, like this, and you continue building them in an intricate way and create something very complex, like a castle and a spaceship. Now the thing is like it says like, is it possible for every complex shape like this spacecraft and this castle can be formed from a simpler block like this? So this is the like conjecture. What it says is, so like in the mathematical term we can say like this every complex structure like what we have said, castle and all, we call it like algebraic varieties, complex structures are algebraic varieties, and this simple shape and this complex these algebraic varieties are defined by polynomial equations, and the simple shapes are called algebraic cycles. Now the thing is, can every complex varieties be built by a simple algebraic cycles. So if we are able to prove it, then again we will understand deep understanding of mathematics and its impact on other subjects. So it's what it says is uh, like consider a building block of complex structure with a Lego structure. So now we build a complex structure with it. So now it's like directly like saying like, can like this more complex structure may also be built with a simple like this Lego builder. That's the thing. You will like understand deep understanding of the universe. So this is a Hodge conjecture. I try to like manifest in a very easy way. So now let's understand another 7 million problem, which is Yang-Mills problem of mass gap. Think like you are like building a wall. Okay, think you are building a wall and it have very small building blocks. Like this is a building block. Okay, now think there are small blocks. No, the walls are made from small blocks like this. No, these are the wall blocks that made the block. So what it says is Yang-Mills problem says this building block like really exists. What we need to prove is like these building small blocks are really there. Existence of this building block are really there, and plus, and these building blocks are like have a force within each other like exist, and this building block are like forcing each other away from each other like this forcing away each other, and this building block have a very little mass. So basically what we need to prove is building block exists. First of all, building block exists. And second is these building blocks have minimum mass. So if you go in physics terms, so consider in the atomic level, okay, so the what we can say in a quantum level, existence of this like the God particle, we can say existence of God particle and the mass of this not a God particle, we can say like electron and all really exist, and they have a very, very little mass. We need to like prove that. So this is a Yang and Mills problem. Now let's talk about another problem, which is Navier-Stokes equation and existence of smoothness. So I'll again like help you to understand this problem with a example. Okay, imagine a river flowing. Okay, imagine a river flowing like this, and in this river, no, there are very much molecules of lot of molecules of the water molecules are there in a very complex. They are going over here and here, like they are like having a complex dance. Okay, influenced by one another, like this, like this. So the Navier-Stokes equation are a set of mathematical equations. Okay, Navier-Stokes equation are the set of mathematical equations that describe the fluid's motion. There are equations in physics called Navier-Stokes equation, which helps to describe this motion of the particle in the fluid. So they tell us like the speed and the pressure and temperature of the fluid change over time. But the real problem is, while we can use these equations to the model and predict the behavior of the fluid, while we there are equations. Okay, consider A equation. Okay, there are equation A which describe the motion of this model and predict the behavior of the fluid. But can it hold truth for every situation? Like for every fluid situation, like so that's the thing we need to prove. Can this can the fluid motion uh, when uh, when they have like a sudden jump or like a thing that situation as well, the this properties of the Navier-Stokes equation doesn't change or remain same. For example, basically what we have done is in 2D structure only we have like done the Navier-Stokes equation, but now we have to prove uh, does it come true for 3D structure as well, 3D three-dimensional motion as well of the fluid. So that is the Navier-Stokes existence of smoothness problem. So now let's understand the another like problem, which is the Birch and Schwinnerton Dyer conjecture. So what it says is, imagine like I can like describe in an advanced mathematics terms. It will be hard for me to understand as well, but I will have it describe in very simple terms. Imagine you are playing in a garden. Okay, now you are in a garden and you are interested in planting a tree. Okay, you are in a garden. Consider you are in a garden and you are interested in planting a trees. You are interested in planting a trees. Now there are many specific ways you can plant a tree. How you want to plant a tree? You can plant over here. You can plant it over here, and you can plant over this like making some like walls like this, and you can plant the tree over here as well, like that. But and this pattern might lead to many possible arrangement as well. So and while others might have only a few, but maybe like there are a lot of people who are like planting a trees in this garden. Okay, and and you have a lot of like arrangements, but there are others as well who doesn't have a lot, don't know very much how to plant a tree. So the pattern, this mathematical terms of the pattern are represented by called the elliptic curve, elliptic curve, elliptic curve. So this number of patterns that you are talking about can be represented mathematically in an elliptic curve like this. Okay, so the conjecture what it says is like uh, actually this Bridge and Simerton Dyer conjecture relates this elliptic curve with the rational solution. What is mean by like the conjecture relates the number of rational solution. Consider, okay, this is two x's. Like there are like rational solution means like solution where both coordinates are rational. Okay, where both coordinates are rational. So this type of solution relates behavior of like function called L function. L function. So there is L function. What we have to prove is L function relates the rationality solution of this elliptic curve, the pattern. So we need to show the L function is related to the elliptic curve pattern. If we are able to prove, then we are going to win the $1 million. So if elliptic function is equal to, if this L function is equal to 0, then the curves are infinitely many curves are going to have infinitely many rational points, but if curves is not, L function is not equal to 0, then it's going to have finite rational points. So basically it helps to understand the pattern. The conjecture predicts the like number of rational solution to an elliptic curve based on the behavior of a specific function. So this is the pattern. So now we have talked about Bridge and Seymour-Dyer's conjecture. We have talked about Navier-Stokes equation and existence of smoothness. Then we have young males and problem of mass gap, and then we have talked about the Hodge conjecture and the Riemann's hypothesis, and then we have talked about Poinnier's conjecture. Now, which Poinnier's conjecture, Riemann hypothesis, P versus. So yes, now we will talk about P versus NP problem. So what P versus NP problem says is basically this is based on theoretical computer science. Like what P versus NP problem says, like P versus NP, what we have to do is, like in P is like the probabilistic like probabilistic function, like which can easily be like found, which solution of this like equations can be easily be found, but like NP solution like can be verified easily again. So NP problem, P versus NP problem is the major like unsolved problem in this like theoretical computer science. They're asked if the problem that can be quickly verified can be quickly solved as well. So P is the problem that can be quickly solved. Okay, this can be quickly solved, and NP is quickly verified. Quickly verified, and this is quickly solved. So now we have to understand it. Like we know that the problem which are quickly solved are also quickly verified. So P is a subset of NP. But there are problems which can be verified but hard to solve. So P is not equal to NP. So what we need to prove is, if we are able to prove P is equal to NP, then this problem is solved. NP is the non-deterministic polynomial time and refers to the problem for which the solution can be quickly checked. So as I've said, NP is quickly verified, but P can be quickly solved, and which is a subset of NP, which can be quickly verified as well. But it doesn't mean every like a problem which can be quickly verified can be also quickly solved. But this is the thing which like scientists and mathematicians are very interested in. If these two are equal, then very high difficult solution can also be found. So these are the 7 problems that we have talked about. Thank you for watching this video, and have a nice day ahead.